So hi everyone, I am Debangshu. I am a second year PhD student at UIUC, and I will be presenting our work on relational verification for deep neural networks. This is a joint work done with Changming and Professor Gagandeep Singh. So before going into details of relational verification, I will be briefly introducing what neural network or DNN verifications are. So I guess we are celebrating now. So as we know that neural networks achieve state-of-the-art performance in a lot of different tasks, including image classifications. However, they are not without flaws. For example, it is possible to add small adversarial perturbation to the inputs so that the neural networks misclassifies the perturbed inputs. As you can see in the slides, the perturbed image of the panda gets misclassified as gibbon. The same thing happens with the stop sign as well, which gets misclassified as the speed limit sign. This can be problematic when we consider we are actually using neural networks in safety critical systems like autonomous driving. So we need a way to evaluate the safety of the neural networks. So what to do in this case? One option is easy, is we can just test the neural networks against the perturbed inputs. However, this method has two major drawbacks. First, we can only test with finitely many inputs, and it actually doesn't give any guarantees about the safety of the neural networks. This is where verification comes into picture. So in this case, we formally prove that for all inputs satisfying the input specification phi, the corresponding output satisfies the output specification psi. So this helps us generalize to infinitely many inputs and also provide formal guarantees about the safety of the neural network. Now, however, most of the existing neural network verifiers works with properties that are defined with single executions and are imprecise for relational properties that are defined over multiple executions on related inputs. So this will be the main thing we will be focusing in this talk. So before going into details of relational verification, we'll be introducing couple of relational properties that help us encode a desirable neural network verifiers. The first one we'll be discussing is the robustness against universal adversarial perturbations, or UAPs. So UAPs are input agnostic perturbations. That means we apply the same adversarial perturbation to all the inputs. Actually, most of the practical attacks that are implemented in real life are actually UAPs. This is because UAPs are easy to implement. We can just tamper with the input device such as attaching a sticker to the lens of the camera as shown in the slide to implement UAPs. Now, in this case, what we want to verify, like given a set of inputs I1 to Ik, we want to compute the minimum number of inputs that will remain correctly classified for all adversarial perturbation V within the threshold. Now, given we are applying the same adversarial perturbation to all the inputs, the perturbed inputs are actually related to one another. The second relational property we will be considering is local monotonicity. Before formally defining it, we will see why it is important to verify the monotonicity of the neural network. Suppose we are using neural network to predict housing prices. So in this case, we expect the neural network should predict higher prices for a larger house with more number of rooms, provided all other features remain the same. So this can be exactly encoded as local monotonicity property. So in local monotonicity property, we have a pair of related inputs, say I1 and I2, sampled from a local input region around a given input I0. So in this case, what we want to prove that if I1 is greater than equal to I2, then the corresponding output n of I1 is greater than equal to I2, n of I2. Now, as we can see, the pair of inputs I1 and I2 are no longer independent. They are actually related by this linear constants, which we call as the cross-executional constant. So what are the main challenges for relational verification? First one is, of course, scalability. We know that even for ReLU networks, the non-relational verification or individual verification is NP-hard. So for scalability, we want our relational verifier to sound, but we compromise on completeness to ensure scalability. But and as discussed before, the main point of distinction between non-relational properties and relational properties are these cross-executional dependencies. So it is important to exploit these cross-executional dependencies is to improve the precision of the relational verifier. Now, we will be going over the details of the relational verification algorithm with this illustrative example, where we consider these 3-layer networks with 2 affine layers and 1 activation layer with ReLU activation. We consider a pair of inputs I1 and I2, which comes from 2 different classes. However, we apply the same perturbation V to both of the inputs. Now, what we want to prove in this case, we want to show that for any bounded perturbation V within this threshold, at least one of these executions remain correctly classified. Now, for this example, we construct a product network with 2 copies of the neural network, one for each execution, and we ensure that the same adversarial perturbation is applied to both the inputs, and also ensure the output specification is defined over the output of both the executions. Now, before coming to our algorithm, we will be briefly reviewing 2 of the existing works. First one was published in PLDI 2023. So, in this work, the author do not track any cross executional dependencies, and they reduce the problem to individual verification. And as expected, given they are not tracking any cross executional dependencies, this method loses out on precision. In the second paper, which was published in ICLR 2023, the authors take 2 steps. In the first step, they apply individual verifier to obtain a local linear approximation of the neural network independently without taking any dependencies. Then in the second step, they add a additional constraint that actually relates the inputs of the 2 executions. And finally, they invoke a MILP solver to solve this MILP optimization problem. However, the main issue in this method is while computing these linear approximations, we do not track any, they do not track any cross executional dependencies, so and loses us on this precision. So, what is the major challenge here? So, in this case, we want to track cross executional dependencies not only at the input layer, but at the subsequent layers as well. Now, the question is how to do that. So, in this case, what we observe that the cross executional constraints from popular relational properties actually share a common pattern. If you look at the slides, that we can see that the difference between any pair of inputs is bounded, and we exploit this fact and track the difference between the outputs of coming from different execution at all layers. And this helps us capture the cross executional dependency not only at the input layer, but at the subsequent layers as well. So, in other words, what we want to do, given 2 copies of the same variable from the product network, we want to compute the bounds on their difference. Now, the issue is exactly computing these bounds can be expensive and can, in the worst case, can take exponential time. Now, how to resolve this issue? Instead of computing this exact bounds, we compute an over approximation of these bounds, and we use abstract interpretation for this. And for this purpose, we design a new abstract domain called DiffPoly, which we'll be discussing in the next slide. Now, the new abstract domain DiffPoly, for each pair of inputs, first track the concrete and symbolic bounds on the individual variables, and additionally tracks the concrete and symbolic bounds over their differences. These concrete and symbolic bounds over the differences actually help us exploit the fact that the difference between the pair of inputs is bounded. Now, this concrete and symbolic bounds over the differences are not found in any of the existing abstract domain that are used for neural network verification, and is very specific to DiffPoly abstract domain. And we also design custom transformers for difference of activation functions like ReLU x minus ReLU y, and we also have transformers for other activation functions like Sigmoid, Tanh, etc. Now, with the DiffPoly, we no longer need exponential time. We can compute the bounds of differences of all pairs of variables in just order n cube time, where n is the number of nodes in the neural network. Yeah. So with the bounds on the differences, we compute additional linear constants over the outputs of different executions that actually encode these cross executional dependencies. Now, as you can see in the slide, the convex region that are computed with these additional difference constants are actually more precise than the convex region that was obtained in the baseline methods. So this is essential for improving the precision of the relational verification. So next, we will be going over the overview of our relational verifier, which builds on top of the proposed DiffPoly domain. So given a relational property is defined over k different execution, we first run existing abstract interpretation based verifiers on individual execution independently. This helps us compute the individual bounds on the individual variable and infer constant over individual execution. Then for each pair of execution, we run the DiffPoly analysis to compute the bounds on their difference and infer the difference constants. Then we collect the difference constants for each of the k choose 2 pairs of execution, and finally we add a MILP encoding of the output specification psi to formulate an MILP problem. Note that this MILP formulation is more precise than that obtained by the baseline, because this difference constraints actually allows us to encode the cross executional dependencies between each pair of execution. Now, if you look at the then we invoke a existing MILP solver like Gurobi to solve this optimization problem. Now, if you look at the example we discussed, illustrative example we discussed before, actually Raven was the only relational verifier that was actually able to prove it, while both the baselines failed in that case. Now, we evaluate Raven with both the baseline with standard benchmarks. For MNIST handwritten datasets, we see that Raven significantly outperforms both the verifiers in terms of precision. We observe the same result for CIFAR-10 dataset as well. Now, for monotonicity, Raven is actually the first relational verifier that actually proves this property for neural networks. However, there exists some other works that uses the bounds on the derivative of the neural network to prove this property. However, as we can see in the slides, Raven is significantly more precise compared to all the baselines. Now, we evaluate the scalability of our method with large neural networks that can have millions of parameters. Although Raven is slower than both the baseline, we observe that the main computational bottleneck actually comes from the MILP solver, as you can see, and we are actually able to resolve this issue in one of our follow-up works. So this work, which is going to appear at this year's ICML, what we did, we replaced the slow MILP solver with a custom gradient-based solver that is more scalable, and with this method, we are actually gained a speed up to 60x with a very minute reduction in precision. So we also have another work that is that is under review, which further improves the precision of the relational verifier. Now, we also designed a training method that allows us to train verifiably robust neural networks against universal adversarial perturbation. This is actually the first training method that is capable of exploiting this cross-executional dependencies. Finally, I will conclude my talk with 3 representative slides from the presentation. In the first slide, we defined what relational properties in and why verifying them is important for neural networks. Then we introduced DiffPoly, and with DiffPoly we computed the difference bounds to infer the difference constant that was helping us to encode the cross-execution dependencies. Finally, we describe the overview of our relational verifier. And the code and the full paper are available in the following links. And now I'll be open for questions.
Thank you for the talk. Do we have questions from the audience? So I have a question. So in your talk, you focused on two relational properties, the UAP robustness and the monotonicity. And it seems like it would be very interesting to look at whether what other properties your approach could be applied to, such as, for example, confidentiality of some inputs, like the output doesn't depend on some inputs. So have you looked at that sort of thing?
Actually, we looked at a couple of other relational properties in the paper. We skipped that for the presentation. So another property that can be verified with is fairness. So suppose we want to prove that your neural network's output doesn't depend on some sensitive features like race, or so that can be exactly encoded in our framework, and it can verify it.
Very nice, thank you. We have a question from the audience.
Yeah. So great talk, by the way. I had a question that while perturbating the inputs, there might be possibilities where there is problems like exploding gradient. How do you compute lower bound and upper bound in those cases?
Sorry, I didn't hear the last part.
Maybe speak into the microphone a bit more.
How do you compute upper bound and lower bound in the cases where the gradients might be exploding or vanishing after perturbations?
So what we did, like you are talking about the existing works for monotonicity, which they compute an over approximation of the gradients using abstract interpretation. So like in that case also you can actually compute an over approximation, right? So it may not be like precise, but it gives a approximation of the gradients.
All right, thank you.
Do we have other questions from the audience? If not, I think we'll end here. Thank our speaker again.